All right, I hope you all are doing well today. If you could, please type here in the chat window to let me know that you're present. Thank you all. So what we are going to be kicking things off with today is the concept of leading and lagging sinusoids. This is effectively right where we left off on Thursday when talking with comparing sinusoids. And this will be our first real topic prior to us getting into our frequency domain circuit analysis stuff. All right, so let's say that we have a pair of sinusoidal signals. VA of t will be 5 cosine 3t plus 10 degrees volts, and VB of t will be 8 cosine of 3t minus 30 degrees volts. So these sinusoids are written in a way that we could do a comparison of them. By that, I mean very specifically, both signals are expressed in terms of cosine functions. So we've satisfied criterion 1. Both functions have positive amplitudes. So we've satisfied criterion 2. And both functions have the same angular frequency. So we've satisfied criterion 3. So I am going to try to plot these functions. Please bear with me. I know that my drawing skills are absolutely terrible. So here's time. Let's do VA first. So VA, we have an amplitude of 5 and a phase angle of positive 10, which means we have a cosine that's shifted slightly to the left. So here's my slight shift to the left. So that's going to be the peak value. And then something like this. So this red curve here is VA of t. And now I'm going to try to draw my blue curve here. We have a peak value of 8, and we have a negative phase angle, so it shifted to the right by 30 degrees. So I'm going to call that right here. Oops, I didn't draw this first one tall enough. Let me fix that. Like so. And our blue curve represents VB of t, okay? So how we would compare these signals is we would look at the peaks that are closest to each other, okay? So for instance, we would be comparing this point to this point, okay? All right, so what we can say about this particular set of signals is that VA of t leads VB of t by some amount to be determined, and we'll talk about that in a minute. Or we could say that VB of t lags VA of t by that same amount, okay? So the reason why I'm saying that VA is leading VB is because the red curve hits its peak value at an earlier point in time than the blue curve does, right? Similarly, VB is lagging VA because the blue curve hits its peak at a later point in time than the red curve VA. Now, if I'm being entirely honest, if I represent the sinusoidal signals like this as a function of time, I have a tendency to make mistakes. And I have observed in the numerous students that I've taught this material to, that they also tend to make mistakes when looking at these signals as a function of time. So instead, we are going to develop what's called a phase diagram, which I believe to be a much easier way or much easier representation for us to use to compare sinusoidal signals, okay? So a phase diagram is simply a snapshot of a sinusoidal signal in time. And we typically use t is equal to 0 as our basis here. So in our phase diagram, the positive horizontal axis corresponds to 0 degrees. The positive vertical axis corresponds to 90. The negative horizontal axis corresponds to plus or minus 180 degrees. And the negative vertical axis corresponds to negative 90 degrees. At t is equal to 0, we scroll up here, this cosine of 3t bit effectively goes away and we're left with just a phase angle of 10 degrees. So I want a vector that has a length of 5 and a phase angle of 10 degrees. So that might be something like this. For VB of t, we have a length of 8 and a phase angle of minus 30. So that might be something like this. And what I'm going to do now is I'm just going to continue on with this projection here and continue on with this projection here, because the lengths of the vectors don't particularly matter in this representation, okay? So if we have a diagram like this, and we're trying to answer a question, and let's give a question to answer here. Say, by what angle does VA of t lead VB of t? What we do is we start our measurement from the second signal that's mentioned. So in this case, VB of t, and we start measuring in a counterclockwise direction. So if we measure from here So here, this is the angle that VA leads VB. So measuring in this direction, counterclockwise, is always leading, and measuring in this direction, clockwise, is always measuring our lagging angle. The reason for this is when we're measuring clockwise, we're seeing how far ahead that signal hit its peak. And when we're measuring clockwise, we're seeing how far behind in angles that signal hit its peak. Okay, so in this case, we would have 30 degrees. Sorry, that's just says 3 plus 10 degrees is equal to 40 degrees. So VA leads VB of T by 40 degrees. If we wanted to know by what angle VA of T lags VB of T, we'd simply measure in the opposite direction. So we would start measuring from B and continue going until we hit our vector VA. So in this case, that's going to look like 60 degrees plus 90 degrees plus 90 degrees plus 80 degrees, or let's see, 140 plus 180 is 320 degrees. So VA lags VB by 320 degrees. Now, I want to point something out here. Conceptually, this using a phase diagram isn't particularly difficult. The second thing that's mentioned in the statement is where we start our measurement from. If we want leading, we measure counterclockwise. If we want lagging, we measure clockwise. You all are going to have a few homework problems on this material. And because web work is web work, it's going to seem arbitrarily difficult. What I mean by that very specifically is that web work doesn't know the difference, or actually web work doesn't understand that 0 degrees, 360 degrees, 720 degrees, negative 360 degrees, negative 720 degrees, etc., all represent the same angle. So you might do your analysis using a phase diagram like this perfectly correctly, type in positive 40 degrees for the angle that VA leads VB of T, and web work will tell you you're not right. And it's just the way that whoever wrote the problem programmed it. Instead, what you would have to do is add 360 degrees, which would be 400 degrees. Check that. If it takes this answer, that's great. If not, subtract 360 degrees, which would look like negative 320 degrees, and put in that. I guarantee you web work will take either the answer you come up with, plus 360, excuse me, or the answer you come up with minus 360. You're not doing anything wrong whatsoever if web work tells you you're wrong. Excuse me. It's just incapable of acknowledging that these three angles actually represent the exact same quantity. Okay, so when you're working on these homework assignments and all that kind of stuff like that, do not get discouraged if web work doesn't tell you you're right. Simply add 360. If that doesn't work, simply subtract 360. One of those three things will work. Okay. On your exam and stuff like that, if I put anything like that or a problem like this on your exam, I'm expecting you to use the methodology that I've described here, and you'll get the obvious answer. So in this case, 40 degrees going counterclockwise, positive 320 degrees going clockwise. Okay. All right, so we have reviewed sinusoids. Now we are arguably ready to get into some circuit analysis. And so I am going to title this little bit right here Forced Response due to sinusoidal signals or sinusoidal inputs. Let's call it that. Devarier, let me go back and let me absolutely answer that question. Sorry, I didn't notice it in the chat. So Devarier asked, does the direction of vectors matter on the phase diagram? Like if VA of t or VB of t had a negative sign in front of them? And the answer is absolutely yes. So if VA of t or VB of t had a negative sign, you should convert that negative into a positive by shifting your phase angle by plus or minus 180 degrees. That was criterion 2 of comparing your signals. So all signals have to be expressed exclusively as sine or cosine waves. All signals have to be expressed with positive amplitudes, and all signals have to have the same frequency. So if you need to get rid of a negative sign, simply shift by 180 degrees in either direction, and that will take care of it. Thank you for your question. All right, so we talked very briefly about the concept of forced response when we were talking about transient analysis. We're going to revisit it here today very briefly as well, okay? So let's say that I have a simple DC circuit where I have some DC voltage Vs connected in parallel to some resistor R, connected in parallel to some resistor C. And I want to know the response of this system, which I have determined will be the current I leaving the voltage source, okay? So in this DC circuit, we can use our DC circuit analysis techniques to find that our current I, in this case, would simply be Vs over R. So if we excite our system with a DC signal, like this voltage source, we get out a DC signal like this current. So it stands to reason that if I have an AC circuit, literally the exact same type of circuit where we have a time varying voltage source, Vs of t, in parallel with some resistor R, in parallel with some capacitor C. If Vs of t is a sinusoid where it has some magnitude Vm, cosine, some angular frequency omega, and some phase angle theta v, our response I of t should be of the form Im cosine omega t plus theta I. So effectively what I'm saying here is that if we put a sinusoid in, we should expect to get a sinusoid out. The magnitudes of the sinusoids will probably be different. The phase angles of the sinusoids will probably be different. But if we excite the circuit at a particular angular frequency, our response will be of the same angular frequency. Okay. I'm going to prove this to you using a numerical example. Okay. So let's say that R is 10 ohms and C is 25 millifarads. Let's say that VM is 12 volts. Omega is 5 radians per second. And theta V is 10 degrees. Our goal here, then, is effectively to determine IM and theta I. All right. So how we are going to analyze this circuit, or how we're going to kick things off really, is to use Kirchhoff's current law. So I'm going to call this current IR of T, and I'm going to call this current IC of T. And using KCL, we can see that I of T, our signal of interest, is simply IR of T plus IC of T, which is nothing more than VS of T over R plus C dVs by dt. And now let's put in some numbers here, okay? So we're going to have 12 cosine 5t plus 10 degrees volts divided by 10 ohms. And then we're going to have 25 millifarads times the derivative with respect to time of 12 cosine 5t plus 10 degrees volts. Okay. So let's start with the bit on the left. 12 volts divided by 10 ohms is just 1.2 amps. So we'll have 1.2 cosine 5t plus 10 degrees amps. And then over here, we need to take a derivative, right? So I'm going to have my 25 millifarads. I'm going to have 12 volts. When I take the derivative of cosine 5t plus 10 degrees, I'm going to get negative 5 sine of 5t plus 10 degrees. Let negative 5 is the omega value, where omega has units of radians per second. Sine 5t plus 10 degrees. And I'm going to leave the units off here, but a millifarad times a volt per second is actually going to be an amp dimensionally. All right, so now I'm just going to multiply things out here. So I'm going to get 1.2 cosine 5t plus 10 degrees amps minus 1.5 sine 5t plus 10 degrees amps as well. Okay. So what we have found is that our response, instead of being a single sinusoid, is now a combination of sinusoids. So I want to take a pause, take a break real quick here, and I want to look at something using a graphing calculator tool. Okay. So what I'm doing right now is I'm just going to Desmos graphing calculator. And I'm going to type in those two functions. Okay. So let's call it I R of X is equal to 1.2 cosine 5x plus 10. And because this particular graphing thing is expecting our angle to be in radians, I'm going to multiply that 10 degrees by a factor of pi over 180, which converts that signal, or converts that whole angle into radians. I guess I'm going to call this I1 just because it's not letting me use IR. So this red curve right here represents our current flowing through our resistor. I2 of X is negative 1.5 sine 5x plus 10 degrees. And so again, I'm going to multiply by pi and divide by 180. And so that's what our capacitor current looks like. And I'm going to add these two together and just say that I of t is simply I1 plus, and actually I need to call that I of X or it's going to freak out, plus I2. And I'm going to turn off I1 and I2. So what I am attempting to illustrate to you all here is that the sum of those two sinusoids, or the combination of those two sinusoids that we developed, one for the capacitor current and one for the resistor current, can be combined together into a single sinusoid with a single amplitude and a single phase angle, which is exactly what we have right here. Now, in order to do that, it's going to take a fair amount of trig, which is why I introduced all those trig identities to you all. Okay. So we're now going to go through the steps that are needed. I'm going to write down the two trig identities that I'm going to start things off with. So if I'm not mistaken, identity number 5 said that sine of x plus y could be written as sine x cosine y plus cosine x sine y. And trig identity number 6 said cosine x plus y was equal to cosine x cosine y minus sine x sine y. Okay. In this case, x is just 5t. And y will just be 10 degrees. Okay. So applying trig identities 5 and 6, what we're going to find is that I of t will be equal to, so let's start with trig identity number 6. So 1.2 cosine of 5t plus 10 degrees is going to look like 1.2 cosine 5t cosine 10 degrees minus 1.2 sine of 5t sine of 10 degrees. And we're going to subtract from that expression, and I'm going to do this on a separate line because I ran out. So this is all one mathematical statement. 1.5 sine of 5t cosine 10 degrees plus 1.5 cosine of 5t sine 10 degrees. Okay. So I applied trig identity number 6 to convert my cosine function into this guy right here. And I applied trig identity number 5 to convert my sine function into this guy right here. What I'm going to do now is I'm going to group like terms. Okay. So for instance, I have a factor of 1.2 cosine 10 degrees minus 1.5 sine 10 degrees multiplied by the cosine of 5t. And then I have a factor of negative 1.2 sine 10 degrees plus 1.5 cosine 10 degrees multiplied by the sine of 5t. Please check my algebra here and make sure I didn't mess anything up, right? So I should have 1.2 cosine 10 degrees with a positive sign from this guy right here. I should have 1.5 sine 10 degrees with a negative sign from this guy right here. Oh goodness. Because the negative sign out front gets distributed. I have negative 1.2 sine 10 degrees times sine 5t from this guy right here. And I have an additional negative 1.5 cosine 10 degrees from this guy right here. And then I'm just taking that negative sign out and distributing it on the left-hand side here. Okay. So as a final-ish step here, or an intermediate step with an important result, this is going to look like 0.921 cosine of 5t minus 1.686 cosine of 5t. I'm going to put I of t out here, and I'm going to put a box around this. Okay. Now this is not the final answer that we're looking for, because we still have a sum or a combination of sinusoids, but at least we've gotten rid of our phase angles, okay? Now, why this is a very important intermediate step is because this is the form, and this is just using trig identity number 6 again. I am cosine 5t cosine phase angle theta I minus I am sine 5t sine theta I, where this 0.921 represents I am cosine theta I, and this negative 1.686 represents I am sine theta I, okay? Thank you. It should be sine 5t. Thank you so much, Sydney. I made a mistake there. Thank you for bringing it up. Let me write that better. There we go. Thank you so much. All right, so our ultimate goal is to figure out what I am and theta I are. So we're actually in a very good position to do that now, okay? So what I mean by that is I am cosine theta I squared plus I am sine theta I squared is equal to I am squared times cosine squared theta I plus sine squared theta I. Use the right bracket here. And I believe we all learned in our trig classes that cosine squared plus sine squared is just equal to 1. So from this, we can say that I am the magnitude of our current response is just the square root of I am cosine theta I squared plus I am sine theta I squared. And wouldn't you know it, we just figured out what I am cosine theta I and I am sine theta I are. So our magnitude is 0.921 squared plus negative 1.686 squared, which comes out to be 1.921 amps. So we've got one thing taken care of. Now I can say that the tangent of theta I is equal to sine of theta I divided by the cosine of theta I. I don't know sine of theta I or cosine of theta I, but if I put I am sine of theta I in the numerator and I am cosine of theta I in the denominator, I do know those quantities, and these I am's cancel each other out. So I can say that theta I is simply the inverse tangent of Im sine theta I over Im cosine theta I, and substitute my numbers in here. Negative 1.686 divided by 0.921, and I get this angle to be negative 61.340 degrees. Putting these results together, I can then say that I of t is equal to 1.921 cosine of 5t minus 61.340 degrees amps. All right, so how long did it take me to do that? Ballpark it. "20-ish minutes. That seems reasonable. Now I can do it faster if I'm not explaining it to you guys. How long do you think it would take for you guys to come to this result? Probably significantly longer than the 20-ish minutes it took me. Okay. If we had to analyze every circuit like this, electrical engineering wouldn't exist. It'd be too tedious for people to practically do. Okay. So what I want to do is I want to revisit something. So I'm going to scroll up here and I'm going to copy something. The result I'm copying is this guy right here. We're going to come down to the next page. I'm going to put it on here for you guys. Like so. I'm going to write in what this means. And so what we're going to do is we're going to cheat. We are going to cheat by observing something. Okay. The information contained in these signals is the same information that is contained in a complex number. Okay. So I'm going to make a very minor adjustment here. 1.2 cosine 5t plus 10 degrees amps is going to stay the same. And then here I'm going to have 1.5 cosine 5t minus 80 degrees amps. All I've done is just change that second part into a cosine function. Now what I'm going to do is, using Euler's identity, I'm going to say, let me write down Euler's identity again for you guys. I think this was trig identity number 9 that we had earlier. This stated that cosine of x plus j sine of x is equal to e to the jx. I'm going to apply this identity. You may be saying to yourself, well, wait, how the heck are you doing that? But we'll get to that. So I'm going to say that I of t is equal to the real part of 1.2 e to the j 5t plus 10 degrees minus the real part of 1.5 e to the j 5t minus 80 degrees. Now, we're going to use our calculators. And to use our calculators, we have to express these complex numbers in a polar form. Okay. So this is the real part of 1.2 angle 5t plus 10 degrees minus the real part 1.5 angle 5t minus 80 degrees. And as a last step here, which I'm going to explain theoretically what we're doing in just a moment, I'm going to throw this frequency junk away. And I'm going to lump this stuff together. So we're going to have 1.2 angle 10 degrees minus 1.5 angle negative 80 degrees. And I would like for you guys to use your calculators and do that math. So I'm going to do it with you on my TI 36 here. I'm typing in 1.2 angle 10 degrees minus 1.5 angle negative 80 degrees and I'm getting a result, and I feel like I've missed a sign somewhere, so we'll find that in a moment. But the result I'm getting is 1.921 angle 61.340 degrees. Okay. Thank you, Devarier. So all right, so let me talk about what I'm trying to do here, because I've messed up a sign somewhere. All right, so bear with me a moment here. I believe very fundamentally that this sign right here is supposed to be negative 61.340 degrees. I might be mistaken, but it'll be okay. What I'm trying to illustrate is that we got the exact same magnitude as we did right here. And we got the same phase angle as well. Now there's a question of whether or not the sign is correct, and that's on me for making a mistake at some point here that I am trying to find. Inverse tangent. Let me look up here really quickly. Okay, so I think I think I've already found it. So I believe that the mistake that I made here, let me look at this. So this is our trig identity. This is literally trig identity number 6. So we have cosine of x, cosine y, minus sine x, sine y. And then I said the quantity negative 1.686 is Im sine theta I, when according to the trig identity, it should be positive 1.686, which will change this sign here, which changes nothing there, but it will change this sign here, which in turn changes that sign there. So this is supposed to be positive 61.340 degrees. Okay, so we get the same magnitude and the same phase angle as all of that trig and stuff, just using complex numbers to represent our sinusoidal function. Okay, this is the key of circuit analysis in the frequency domain. Okay, I do want to point something else out though. Okay, I circled this bit right here in blue, 0.921 minus 1.686 sine 5t, right? If we were to express the complex number that we have right here in rectangular form, we get the real part of 0.921 plus J 1.686. Okay. These coefficients are the exact same thing as the coefficients we see here, except the sign on the imaginary portion is flipped. That is actually correct this time. And it's because of this trig identity. Now, the reason why I'm bringing all of these little relationships up here, we are going to use this complex number representation for all of our circuit analysis because it makes the math much, much shorter. But in your homework sets, you will be given, actually, let me pull one up real quick. Let me get my keyboard out. We're literally going to work on your homework problems. Homework set 19. Because I want to show you how absolutely powerful and wonderful complex numbers are. Okay. So homework set 19, let's look at problem 1. That's actually pretty easy. Let's not worry about that. Now we can use what we learned here on this one as well, but let's look at problem 2. I think it's more difficult. Yeah, problem 2 is a pretty surly and terrible problem. Okay. So we are asked to find A, B, C, and our phase angle given these constraints. I'm going to go back and forth here real quick, copying things down. So we have 28 cosine 100t minus 84 degrees. minus 19 sine 100t plus 15 degrees. And we are told that this is equal to a cosine 100t plus b sine 100t is equal to c cosine 100t plus some phase angle phi. And we're asked to find A, B, C, and phi. Okay. Now, in the example problem that I worked, we effectively did all of the steps of this problem. And it took absolutely forever. So what I'm going to do here is I'm going to talk about a shortcut to solve this problem just using complex numbers. The first thing that I'm going to do is I'm going to change that sine bit into a cosine bit so that we're going to have 28 cosine 100t minus 84 degrees minus 19 cosine 100t minus 75 degrees. The next thing I'm going to do, so this is step one. The next thing I'm going to do is I'm going to express these as complex numbers. So this is going to look like 28 angle negative 84 degrees minus 19 angle negative 75 degrees. And I'm going to throw this in my calculator. 28 angle negative 84 minus 19 angle negative 75. I get 9.700 angle negative 101.843, where this bit is C and this bit is phi. And if I convert my complex number to rectangular form, I get negative 1.991 minus J 9.494, where this bit is A and this bit is negative B. Just to prove it, I'm going to type those answers into Weber. And it should tell me that I've done everything correctly. So A is negative 1.991. B is positive 9.494. C is 9.700. And phi is negative 101.843. So as long as I've typed all those numbers into my calculator correctly, just for the sake of argument, let's check our answers and show the correct answers. Voila. All of those are correct, okay? So we could spend 20 plus minutes doing all of that math using the sinusoids, or we can spend 2 to 3 minutes while we're getting comfortable doing all of that math using complex numbers and get literally the exact same result. It's this simplification and reduction in time. That's why electrical engineering uses complex numbers so much, because doing the math using the sinusoids is horrible, and doing the math using the complex numbers is easy. What we're going to be talking about for literally the remainder of the class effectively is what's called frequency domain circuit analysis, where we take a time domain or circuit like the one that we started off with, and then we work it in the frequency domain just using complex numbers and wind up getting the same result as we would get if we had worked it all using the sinusoids. So I'm going to spend the next couple of minutes explaining why that is, and then I'm going to stop talking. All right. So let's say that we have a linear black box network. And we apply a time varying voltage signal, Vs of t, and we measure some response, I of t. Okay. So I'm literally just generalizing the example problem that we just did. If Vs of t is of the form Vm cosine omega t plus some phase angle theta v, then I of t will be of the form Im cosine omega t plus theta I. We literally just proved that. Now let's say that we take that same black box network and we change things very slightly. Let's call this VS1 and I1 just for the sake of argument, because I'm going to wind up using the additivity property of superposition here in a moment. So let's say that we have some voltage VS2 now. We apply it. We measure some response, I2 of t. Well, let's say that VS2 of t is Vm sine omega t plus theta v. What would we expect I2 of t to look like? So when we put a cosine function in, we got a cosine function out. So I believe that it's reasonably easy to accept that if we put a sine function in, we'll get a sine function out. Probably even more easy to accept if you recognize that sine functions and cosine functions are literally the same thing, except they're just shifted by 90 degrees away from each other. Okay. So what I'm going to do now is I'm going to apply the homogeneity or scaling principle here. So if you recall from our lecture on superposition and linearity, the homogeneity or scaling principle of linearity said that if I scale my input by some non-time varying amount, and I have a linear circuit then I scale my output by that same linear non-time time varying amount. I'm going to scale the input by j, which should in turn scale the output by j. Now, if we take that linear black box network and we apply a combination of our previous results, and we want to know what our response is, using the linearity principle, if Vs of t is Vs1 plus Vs2, which would be simply Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v, which is the same thing using Euler's identity as Vm e to the j omega t plus theta v. Then our output I of t must be I1 of t plus I2 of t is Im cosine omega t plus theta I plus j Im sine omega t plus theta I, or Im e to the j omega t plus theta I. So it's really the superposition principle that allows me to cheat or take that shortcut that I did earlier. What I mean by that specifically is we can observe something that's pretty fantastic here, okay? The real part of this input signal is this cosine function right here, which is just a sinusoidal signal in the time domain. And we can also observe that the real part of our response, or our output, is just the answer that we're looking for. So effectively, we can work these circuits using complex numbers and then only take the real part of our result to get the time domain quantity that we were looking for. Okay, so let's do this briefly here. Okay. We're going to work the exact same problem. Here we have Vs of t. Here's our 10 ohm resistor. Here's our 25 millifarad capacitor. Here's our quantity I of t we are trying to find. And in this case, we're going to say that Vs of t is 12 e to the j 5t plus 10 degrees volts. And we expect I of t to be of the form Im e to the j 5t plus theta I amps. Okay. We're going to do Kirchhoff's current law again. So let's call this IR of t. Let's call this IC of t. And we know that I of t is equal to IR plus IC, which is ds over R plus C dvs by dt, or 12e to the j 5t plus 10 degrees over 10 ohms plus 25 millifarads times the derivative of 12e to the j 5t plus 10 degrees. This is going to look like 1.2 e to the j 5t plus 10 degrees. And we're going to have 25 millifarads. When we take the derivative of this, we're going to take down a j times 5 radians per second times 12e to the j 5t plus 10 degrees. And what we're going to have here then is, let's see, we have 1.2 e excuse me, 1.2 e to the j 5t plus 10 degrees plus j. All right, so now we're going to have 5 times 25, so that's 125 millifarads per second multiplied by 12 volts. So 0.125 times 12 is 1.5. E to the j 5t plus 10 degrees, like that. And now what I'm going to do is explain to you what it means to multiply by a factor of j. But I just want to make sure that my math here is correct before we go charging along. So 12 over 10, that makes sense. C times the derivative. So the derivative of e to the j 5t plus 10 degrees. So that's the derivative of e to the alpha is looks like alpha e to the alpha. In this case, alpha was j5t. So j5. So that's why I pulled down that j5. So that all looks to check out. All right. So okay, so what I'm going to do here is explain what I'm going to do with that j out front. I'm terrified I made a mistake in my last thing, but it'll be okay. So this is my complex plane. Here's my real numbers. Here's my imaginary numbers. If I go out 1 unit in the real direction, this is the same as 1 plus J0. Sorry, there shouldn't be a degree sign there. Or 1 angle 0 degrees. Or 1 e to the j 0 degrees. Well, if I go out 1 unit in the imaginary direction, this is the same thing as j, or 0 plus j, or 1 angle 90 degrees, or 1 e to the j 90 degrees. So if I treat this j right here as multiplying by a factor of e to the j 90 degrees, then what I get is 1.2 e to the j 5t plus 10 degrees plus j, sorry, taking that j out, plus 1.5 e to the j 5t plus 10 plus 90 is 100 degrees. Okay. All right, so what I'm going to do now is I'm going to write this whole thing out here. Okay. So we have I of t, which is Im to the j omega t plus theta I is equal to 1.2 e to the j 5t plus 10 degrees plus 1.5 e to the j 5t plus 100 degrees. Now I'm going to break my exponential functions up. So I'm going to have Im e to the j omega t e to the j theta I is equal to 1.2 e to the j 5t, sorry, and this, yeah, e to the j 10 degrees plus 1.5 e to the j 5t e to the j 100 degrees. This, and this all cancel out because they represent literally the exact same thing if omega is equal to 5, okay, which we know it must be. So effectively, what I have here is Im e to the j theta I is equal to 1.2 e to the j 10 degrees plus 1.5 e to the j 100 degrees, or Im angle theta I is equal to 1.2 angle 10 degrees plus 1.5 angle 100 degrees. If I throw this into my calculator, I get 1.921 angle 61.340 degrees. So we did less math, no trig identities, and got the exact same result as we got using all of those trig identities and stuff earlier, okay? This representation, though, was a little bit more tedious than it needed to be, okay? So what I'm going to introduce on tomorrow's lecture will be our formal treatment of circuits in the frequency domain. And we're going to do that by using what are called phasors. where a phasor is just a shorthand representation of a time domain signal. All right, so that's enough out of me for today. Hopefully I have, at the very least, convinced you not to analyze sinusoidally excited circuits in the time domain. And we are going to tie this theoretical mumbo jumbo up at the beginning of our next meeting and get into the much more simplified version of circuit analysis using complex numbers. All right, thank you all.